Yeah, so and I'm going to be taught, so that's it, so I'm starting. So this is about accessible infinity cosmoi, which is joint work with Steve Lack, building on work with Lukáš Foxinek, which is very recent. So I'll just start with an introduction, some sort of classic stuff. So how do we know that sort of algebraic categories, e.g., are co-complete? Okay. So, for example, groups, rings, etc. Well, so one way is to show, for instance, that they have limits. So this is easy because limits are well behaved, so they're just like they are in sets. And so we can add to that the fact that the category of groups is accessible. So this is also pretty, can people hear me okay? And things like that? Okay, good. So group is accessible. So this is also sort of okay, at least. And why is it okay? It's okay because filtered colimits are also well behaved. Apologies for the handwriting here. Though that's a bit of an exaggeration. There's still some work to do to show accessibility. But anyway, so once we have that, then there's a nice theorem, which is that accessible plus complete, meaning plus having limits, implies co-complete. Okay, so that's one way you can show. Sort of what it's saying is that we're interested in these co-limits, which are kind of complicated. Now we've got limits which are easy, and well, we've got this accessibility thing, which is not too bad. And from the two of those, we can get co-limits, which is kind of nice. So that's one way you can see algebraic categories have co-limits. So another similar question is why do algebraic functors have left adjoints? Okay, so that's a similar sort of question. So for instance, we might look at the forgetful functor from rings to groups. I was just teaching this sort of thing in Algebra 3, actually. I'm not sure it was entirely appropriate for the course or a bit categorical, but there you go. So that's why I'm thinking of this stuff. So, well, they clearly preserve, such functors clearly preserve limits, okay? Which is again easy because limits are well behaved. And also filtered colimits, which is again easy because filtered colimits are well behaved. And now there's a theorem which says that if you have an accessible functor, so what does that actually mean? So accessible, that means it preserves lambda filtered colimits for some lambda. So if you have a functor like that, and it also preserves limits between accessible complete categories. Of course, these are also the locally presentable categories. Then U has a left adjoint. Okay? So we can apply, so that's one way you can see these sort of things, okay? So we can use sort of right universal stuff, limits, to get left universal stuff, like colimits and adjoint functors. Now, so what if we pass from, say, from sets with structure to, say, categories with structure, or perhaps infinity categories with structure. For example, we might ask, what about the two category? What about the two category of monoidal categories and strong monoidal functors, ones which preserve the structure up to isomorphism? Can we say that it's co-complete in some sense? Or what about perhaps the infinity cosmos? So this is a certain simplicially enriched category, which I'll remind you of in a moment. For instance, of quasi-categories, also called infinity one categories, with finite products, okay? So the goal for today, answer these sorts of questions focusing on the infinity cosmos, so the infinity categories setting. Okay, so that's the goal for today. Okay, and so the overview, just for, you can see where I am on the page. So an overview is, first I'll remind you about infinity cosmoi. Then I'll talk about accessible infinity cosmoi. And finally, I'll talk about the adjoint functor theorems and co-completeness, which is based on joint work with Lukács Bokszczynek. Let's see here. Okay, so let me see. Okay, good, I can see people now. If anyone has any questions, feel free to ask me one, or if things are not clear. Okay, so that's the plan. So let me remind you about, or tell you a little bit about these so-called infinity cosmoi, which are introduced by Real and Verity. Okay. Well, I'm not going to give you the full definition, but an infinity cosmos C is a certain simplically enriched category. The other thing it has is a class of isofibrations. So, which we write sort of like this, with two arrows, or two heads to the arrow. So what else does it have? So each CAB, each HOM is a quasi-category. So of course it's enriched in simplicial sets. So, but we ask furthermore, that it's a quasi-category. So the other main thing is that C has some limits, okay? E.g. Products, powers, some nice, basically limits that are homotopy limits in some sense. So the other one, which people might be familiar with from model categories, is that you require pullbacks of isofibrations. They're sort of homotopy limits, and also countable composites of countable towers of isofibrations, so the limit version, but we won't talk about that. Plus some further properties. Okay, so what's the idea of it? The idea is that infinity categories themselves tend to assemble, at least in good cases, into an infinity cosmos. So amongst the basic examples, we have the simplicially enriched category of quasi-categories, or infinity one categories, as they're sometimes called. So another case would be there's a infinity cosmos of complete Seagal spaces. This is another model for infinity one categories. So the idea is you can put different sorts of infinity one category in these things, and you don't have to worry about what it is. So another simpler example would be categories in functors. So just cat. Okay, so if you don't know much about all the infinity stuff, then you can just think about cat and think about whether the things I say are true when we take cat. And in fact, a large part of the story is rather too categorical. And that's based on the starting point that each quasi-category, remember we're enriched in quasi-categories. So each quasi-category has a homotopy category. So this is a certain simplicial, so the quasi-category is a certain simplicial set. And what we can do, so it has sort of objects and arrows, and then we can modulo those arrows out by higher dimensional cells, and we get an ordinary category. So we get this homotopy category. And it follows, so it has the same, say, objects, zero simplices. So it follows from this, basically, that each infinity cosmos C has a homotopy 2 category, which we can call HC, okay? With with the same objects as C, and how do you define it on HOMs? Well, we've got this HC, and we have to say what its HOM categories are. Well, we just define these to be the homotopy category of the quasi-category that is the HOM. Okay, so in particular, so the important thing is that HC now has the same objects and arrows as C. Okay, it's two cells are equivalence classes of say arrows in these HOM quasi-categories. So the cool thing about this is that it means we can import lots of 2 category to study these to these infinity cosmoi. So for example, we can define a morphism in C to be, for instance, equivalence or left or right adjoint if it is one in HC, which is a 2 category. And you see, you can define, there's a whole theory of equivalences and adjoints and stuff in 2 category theory. So this enables us just to import all of that to study these different notions of infinity 1 categories. And yeah, so maybe let me, since I've started with my red pen, I'm going to highlight the key points as we go along. Yeah, so homotopy 2 category. So we can define things to be equivalence if it is 1 in C. And important, perhaps surprisingly, this captures this 2 categorical sort of quotient captures the correct notions of correct infinity categorical notions of equivalence and infinity categorical notions using just 2 category theory. Okay, so what else can we do? So an important point is we can also can talk about things like limits in an infinity category. Remember, we think about the objects of an infinity cosmos. Some real and verity call them an infinity categories, just as a sort of generic name. And we like to talk about limits in an infinity category. So we can say that an object of an infinity cosmos has limits of, say, shape X for X's simplicial set. If the diagonal map from A to the X, remember you think of A to the X as being the Functor category. This is what we usually do. So if you have this diagonal map, so this is induced by the map from the unique map from X to 1. Remember that an infinity cosmos, well, so and these guys are, this is the power by the simplicial set. Remember that an infinity cosmos has powers by arbitrary simplicial sets. So we have these constructions available. And so we say that A has limits of shape X if this diagonal map, which always exists, has a right adjoint, because we've defined right adjoint already. Right? So now so what we're doing here is very easily defining all these infinity categorical notions, just using a bit of 2 category theory, and then we can prove, for instance, things like, I'm going to use this terrible abbreviation that I never use myself, just because I never understand, just because I'm trying to abbreviate everything. So RAPL, right adjoints preserve limits. You can prove it just using sort of the usual, say, 2 categorical proof. I'll come back later. Sorry. Okay. And so this applies to many notions of infinity 1 category. So these proofs apply to the different notions. And this is what, say, this term model independent means. If I understand it correctly. Okay, so you can prove things in this setting that will apply to the different notions of infinity 1 category, for instance. So now that's just a little bit of an overview of what Infinity 1 categories are about. So I'm going to have to, before I get on to the accessible Infinity category stuff, I need to tell you a few more technical things because I'm going to use them again later. But so there's a morphism of infinity cosmoi, and it's what you think it should be. So it's an enriched functor which preserves all the structure. So the isofibrations and the defining limits, of which I told you some. Okay. I didn't name it, sorry. What am I trying to say here? This is the definition of a cosmological functor. So this is the morphism of infinity cosmoi. Okay. All right. So I'll just have a sip of water. If anyone wants to ask me a question, feel free. All right, so those are the basic ideas of infinity cosmoi. And now, one more thing I want to tell you about is a bit more technical. This is really about how we know that there are lots of examples of infinity cosmoi. Okay, so the core thing, the core building block, if you like, of examples of these things is that if you have a model structure enriched over the Joyal model structure on simplicial sets, in which all fibrant objects are cofibrant, then the full subcategory of fibrant objects is infinity cosmos. Okay, so this implies, for example, that QCAT of the quasi-categories, and also, for instance, that CSS of complete Seagal spaces, and also, I guess, CAT are infinity cosmoi, though the CAT case would be easier to show just directly, certainly. Okay, but this gives us a core group of examples. Now I want to tell you about how you can construct from new infinity cosmoi from old ones. So I'm going to tell you a few of the core constructions. So if you have an infinity cosmos C, then you can construct an infinity cosmos of isofibrations. Now, the objects of this are the isofibrations. The morphisms are commutative squares. And so the isofibrations in this thing are sort of the ready isofibrations. But that doesn't really matter. I'm not going to get into that. But this is a very important example. Similarly, you could, for example, slice the isofibrations over an object. Over a particular object. Okay. you couldn't, for example, as far as I know, form an infinity cosmos just of arrows. That would be problematic. So, all right. So a rather obscure sounding example, but arguably the most important one. Well, for the sorts of things I want to talk about, is the infinity cosmos of maps having a right adjoint, right inverse. What does that actually mean? I.e., the co-unit of the adjunction is invertible. Sounds a bit obscure. I actually sometimes call this Lally, but I'm changing my notation here to follow Emily and Dominic. Okay, so this is very obscure, but you should think of, for example, these guys are stable under pullback, but you wouldn't be able to pull back a general adjunction. Right. So we have these raries, but the important thing is that this is not a full subcategory. So the morphisms are the morphisms of adjunctions, right? So what does that mean? You have a commutative square whose mate is invertible. So, okay, and so this is very important. So this is not full. And these non-full examples, if you like, are a bit trickier, perhaps. Okay, how are we looking? Good. So there's one other core construction I need to tell you about. So if you have a pullback square, like this, okay. If this is a pullback of simplicial categories, and everything's infinity cosmos. So if L, K, and K prime are infinity cosmoi, okay, and we'd want F cosmological and I a cosmological embedding. So I haven't told you what this is, but it means it's injective in objects, injective in arrows, full in other dimensions, and sort of homotopy replete, so closed under equivalent objects and things. But you don't really need to know. You just need to know that we can construct new infinity cosmoi using certain pullbacks. And moreover, F prime, I guess, cosmological, and I prime cosmological embedding. Okay, so now these are all some, don't worry, you don't really need, in a way, you don't need to know this stuff. But the point is that these are the core, perhaps, or at least the core ones that I've noticed from Real and Verity's book, the core constructions of infinity cosmoi. So you can build lots of new ones from old. So from these ones, you can construct, for instance, the, it's supposed to look like that, I think. The infinity cosmos of infinity categories with limits or colimits of shape X. So if you think about that for a second, you'll see, well, we say, you can say that an object has limits of shape X if a certain map is an adjoint. Well, you can in fact do it if you say that a certain map is a right adjoint, right inverse. And so that enables you to build these things from the rarities and these pullbacks. So we can also similarly construct things like the infinity cosmos of Cartesian fibrations, and or two-sided discrete fibrations, or whatever you like. You can build lots of things. Okay. So what you need to take away just from this page, which I'm going to try and copy and use it again later, we should take away from this page is that there's a few core building blocks of infinity cosmoi, and from these there's a few core constructions, and putting these together you can build pretty much all the stuff you want. So that's what I wanted to tell you about everything I wanted to tell you about infinity cosmoi. So now we're ready for accessible infinity cosmoi. So what's the definition? This is the main thing today. So in infinity cosmos, C is accessible if one. So the first thing is C is accessible as a simplicially enriched category. Okay, so there are in fact, so this would be following sort of the definition that Lack and Rositzky used a few years ago in their paper Enriched Weakness, which well, first it means that you sort of have every object an ordinary filtered colimit of finally presentable objects. These objects, that has to be an enriched filtered colimit. Yeah, the objects have to be finally presentable in the sense that homing out of them preserves enriched filtered colimits. There's also a different notion due to Bourke and Quintero, I think, which is also interesting, but I'm not sure what the relationship is. But here, the way to think about what we're doing here is thinking of enriched categories as categories with properties. So in particular, enriched categories with powers are maybe more like categories than genuine normal enriched categories, because they're sort of, anyway, closed modules in a sense. But so what I'm trying to say is that in the world of enriched categories with powers, you get a better understanding of these things. So to be an enriched category in this sense is just to say that the underlying category is accessible, and moreover that each powering functor is accessible. Remember that in infinity cosmos we have powers. Okay, now that's what it amounts to ask that C is accessible, but we also require that the full subcategories, these are ordinary categories, well, I don't even need to give it a name actually, of the RO category containing the isofibrations and the equivalences. Remember, we defined equivalences earlier in the two categorical way, are accessible. and accessibly embedded, in the sense that the inclusion of these full subcategories preserves sufficiently highly filtered colimits. Okay? And so why do we want these additional properties, right? So why do we need this sort of stuff? These extra things in 2? Well, the first observation is, well, we want our notion of accessible infinity cosmos to be stable under the various constructions that I indicated last time, because we want there to be lots of accessible infinity cosmoi. And so in particular, if we want the infinity cosmos of isovibrations to be accessible, we're going to want that the full subcategory of isovibrations is accessible and accessibly embedded. So that's pretty clear. So what about equivalences? Well, some people might think, okay, this is clear enough as well. It's just like in a combinatorial model category or something, though things are sometimes phrased in terms of trivial vibrations, which you can do here as well. But really so it took a while to work this out, that the core thing, which is actually not that easy to prove, is that this property is equivalent to, or really we just need that it implies for the purpose of proving things, is that it implies that there exists some regular cardinal lambda such that lambda filtered colimits are homotopic colimits. And this is very important. So now if you think about what it says that every object in an accessible infinity cosmos, well, we know that every object is a filtered colimit for some lambda of lambda presentable objects, but now we know that this is actually a homotopic colimit as well. So it's a well-behaved colimit. And so what does that actually mean? I should define what I mean by a homotopic colimit. So if J is a lambda filtered category, and D a diagram of shape J, so let Q to delta 1 be the cofibrant replacement, so it's independent of the choice of cofibrant replacement. The cofibrant replacement of terminal weight as delta 1, then what we need is that I'll just write it down. So maps out of the usual colimit are the same as things like this. So this says that ordinary colimits are weighted colimits by the, maybe I can copy that and use it again. So we have a map like this, and we require that this is a equivalence of quasi-categories. So that's what it means. So both the left-hand side and the right-hand side are automatically quasi-categories, so we can speak of an equivalence. Now, so this is a strengthening, if you like, of the notion of a filtered colimit, which says the first part is an isomorphism. Now we're saying what this second part being, the whole thing being equivalence says somehow is that these filtered colimits are also well behaved with respect to homotopy cocombs. Okay, well, I'll explain why.
John, may I ask you a question?
Yeah.
What is the lambda for which this happens in infinity categories? So in Q-cut?
the smallest one. Because equivalences are closed under filtered colimits. If I'm pretty sure. I haven't really been thinking about that aspect. Okay. So now, hopefully this works. Oh, where's my paste option? So copy, paste. Oh, I've skipped a page. I copied the wrong page today. Sorry about this. Constructions of, copy. Paste. Okay. And
a question, John.
Yeah.
So it doesn't surprise me that you'd want an extra axiom about the isofibrations being accessible and accessibly embedded, because that's kind of additional structure, not canonical in any way. But you can characterize the equivalences in an infinity cosmos as, if you like, the representably defined equivalences, or using some kind of homotopy equivalence notion that involves the cotensors. So I am a little surprised that it's not a theorem that if you have an accessible infinity cosmos in your sense, with all the definitions except the equivalence one, that is included.
Okay, well, it could be. So I don't know how to.
So you'd have to prove it for quasi-categories, for using model, maybe, using accessible model category stuff. Giorgi probably knows a proof of that. And then from there, I suspect, or it would surprise me if you couldn't bootstrap the equivalence property to.
Well, maybe, okay, so it's possible, but maybe let me explain where it's going to be used, which is sort of about bootstrapping.
Yeah.
So, but okay, so let me run through what happens for accessible infinity cosmoi. So certainly if we have combination.
Yeah, in any case, I'm not quibbling with the fact that should be true.
No, but it's an interesting question. So if we have a combinatorial model category, then C5 is an accessible infinity cosmos, okay? So all of these basic examples are accessible. So again, if C is an accessible infinity cosmos, so is this C5. Okay, same for this. So this is a bit tricky. Well, it's not that tricky once you know how to do it, but it took a bit of thought. So I'm going to try and explain what the idea is for that in a minute, because this RARI thing is somehow the core example if you want to get structures defined by universal properties. But it's true, right? So if this is, so this is an accessible infinity cosmos, and if we have a pullback of accessible infinity cosmoi, but accessible everywhere, then things will work again. So this is, if you like, let me expand this a bit. The Mackay-Pere limit theorem is the core for this because, so these are pullbacks of accessible functors between accessible categories and this cosmological embedding will be an isofibration in the usual sense. This is a bilimit. So basically what I'm saying is that all of our constructions are stable for accessible infinity cosmoi. Okay, so all of the examples are accessible for things that you can construct using these. Let me see how much I've got left. So I don't have too much left. I might go on to 5 or 10 past, so I apologize for that. But I'd feel a little bit bad since Emily came and sort of about and Dominic's stuff, I should try and explain at least one bit of the proof. So how do you prove the Rari thing? Okay, so I'm not in fact going to prove that. I will just prove an easier case with a similar proof. So if you think about the proof for this case, then you'll get the idea of how to prove the thing for Raris. So the confusing thing is this case does admittedly admit an even easier proof, but don't think about the easier proof. Think about this proof. So consider the sub-infinity cosmos of discrete objects. Also, confuses me about whether they're discrete or groupoidal. So for, well, let me just stick with discrete objects. So what does this mean? So I understand, I think, where the term comes from. But X is discrete by definition if and only if CAX is discrete. My apologies, I mean a Can complex for all object A. Okay, so this is a representable sort of definition. And now the thing I want to do is to claim X is discrete if and only if CBX is discrete for lambda presentable object B, okay, for some lambda. So how do we prove this? Well, there exists lambda such that lambda filtered colimits are homotopy colimits. Okay, so for a general object A, write it as the colimit over the AI of some lambda filtered diagram, and then you can hom from A into X. So this is then becomes a limit, a homotopy limit. It's a homotopy limit of discrete objects in QCAT. Okay, and now, so disk for QCAT, for example, is a cosmological embedding. So it's closed, say, under flexible limits and stuff like this, but because it's homotopy replete, it implies that it's closed under homotopy limits. Okay. And therefore, as the CAIX are all discrete, it implies that CAX is discrete. Okay, which is what we wanted, and that means that X is discrete. So the point, to summarize that, so what that enables us to do now is to reduce from a large class of representing objects to obtain disk C as a pullback over the lambda presentable objects. So these things are now, on the right-hand side, are going to be accessible categories. Okay. So this is going to be a pullback of accessible categories. And then you can apply the Mackay-Pare theorem. So it's an accessible infinity cosmos. And so what the homotopy colimit condition enables us to do is to reduce four representable types of definitions from representations with a large collection of objects to a small one, and then to describe these categories as pullbacks and apply and deduce their accessibility that way. So you can do something similar in spirit for the raris, and yeah, that's the idea of that. And now let me finish for a few minutes talking about the applications of this. And so this is a direct application of our work of our joint paper with Steve and Lukáš Vokšinek is here as well, Adjoint Functor theorems this year for homotopically enriched categories with Steve and Lukáš Vokšinek. Okay, and so what we did in this paper, I'm not going to tell you too much about it, but instead of working with simplicial sets, we worked for a general monoidal model category V, and we worked out all these, we studied categories enriched in V. And so here, and we did all these adjoint functor things and stuff for that setting. So here I'm just going to interpret our results for simplicial sets with the Joyal model structure. And so specialize from accessible simplicial categories. So all our results worked for accessible simplicial categories with cofibernally weighted limits to accessible infinity cosmoi. Okay, and so our two theorems interpreted at this setting are, well, let me call theorem one the co-completeness one. So I won't define the terms properly in this. I will do in the second one about the adjoint functors. Though the terms I use in this statement will have been defined by real and verity. So, so suppose you have an accessible infinity cosmos, then A has flexibly weighted homotopy colimits, which are the sort of appropriate notion of homotopy colimit there. In fact, we prove rather more than this. We also prove, for instance, that they have any sort of homotopical versions of any colimit. So they have homotopy coequalizers. That means you can form a coequalizer cocone for any diagram, but it'll only have a weaker universal property. But so this, the notion of flexibly weighted homotopy colimits implies you're using only cofibrant weights, but we don't need the weight to be cofibrant. So let me tell you the adjoint functor theorem. Suppose we have accessible infinity cosmoi and accessible cosmological functor. Then U has homotopical left adjoint. In the sense I will say now. So again, I don't have a name for these things. I'm just writing homotopical for this talk. So for each object of B, there exists some object, let's call it FB, and unit map as usual, such that for all objects of A, the morphism from FB to A, or the morphism of simplicial sets, which does the usual thing. It takes a map and returns this. Eta alpha is, well, we actually prove it's a surjective equivalence of quasi-categories. We have this notion of shrinking morphism actually, which, okay. Oh no. Okay, and so this is our main adjoint functor theorem. And yeah, so those are the main results. So maybe I'll just summarize. I'm not too far over time. So to summarize, accessible, well, I introduced accessible infinity cosmoi. Most, if not all, well, probably, I'm sure not all, but the basic examples of infinity cosmoi are accessible, and they're closed under the key constructions. So that's good. And finally, hence they admit all of these accessible infinity cosmoi admit homotopical colimits, these flexibly weighted homotopy colimits, and an easy homotopical adjoint functor theorem. So now if you want, you can easily prove that the infinity categories with products or whatever, you know that infinity cosmos of them is co-complete in the appropriate sense, etc., etc. So that's all I wanted to say. And yeah, so how do I stop sharing? So yeah, so stop share. So that's it. Yeah, so thanks. So yeah, if anyone has any questions or any comments, feel free to go ahead. You can unmute yourself and just speak.
Just a comment. I mean, I think this is awesome. So
Thanks.
I mean, it's really useful for just developing the general theory, the fact that infinity cosmoi are closed under these various constructions, you know, particularly kind of Cartesian fibrations and iterated versions of that. You know, stable infinity categories are another example, and just having all of those accessible now without having to go back to the model category theorem is going to be really fantastic. You know?
Okay, cool. No, it's yeah, I mean, the way you did things made things, a lot of it quite easy for us, because the way you do the constructions mixes perfectly with the sort of accessible stuff, and so that's great. And yeah, it all seems to work very well. So yeah.
So there's one more kind of, there's one more sort of family, or there's one more sort of construction idea of an infinity cosmoi that we're exploring. It's probably not going to get in the book because we're out of space, and I'm the wrong person to talk about this because Dom's thought about it a lot more than I have.
Okay.
But in any case, why not? So there should be some sort of notion of a Grothendieck fibration of infinity cosmoi. So the primary example is the isofibration, the codomain out of the isofibration infinity cosmos down to the base. And a thing to observe is that the fibers, so not only is the total space, the infinity cosmos of isofibrations, the cosmos, but so is the base, of course, that it's a Grothendieck fibration on underlying one categories. The functor itself is cosmological, and then all the fibers are infinity cosmoi, and the sort of reindexing functors between them are cosmological. And there may be something else about to the definition about I don't know what happens when you pull back along an equivalence as opposed to just an arbitrary map. But in any case, so we use so then there are various sub Grothendieck fibrations of that. The Rari one, pulled back is, I guess, the sense I mean of sub. There's the Rari one, or there's Cartesian fibrations versus Cartesian fibrations over a fixed space. And I think there's probably a similar example for other inverse categories. So, an infinity cosmos of two-sided fibrations could be understood similarly from, so two-sided fibration means the right leg is co-Cartesian and the left leg is Cartesian, and some sort of compatibility condition. But that could be realized inside just the infinity cosmos of sort of two-sided isofibrations, and sort of spanning isofibrations in an infinity cosmos. And we sort of secretly use this theorem that it hasn't quite been stated yet in kind of both directions. So knowing already that the total space is an infinity cosmos to conclude that the fibers are, and also knowing already that the fibers are cosmoi, and some things to build this structure on the total space. So anyway, Dom probably has a theorem like that in a notebook somewhere. And so that's the only other construction that is implicitly made use of, but that I'm aware of at present.
I should mention, so when we were originally proving these things for Lallies and stuff, we were using the point of view as the total category of the Grothendieck fibration, where you can define the Lallies as the terminal objects amongst isofibrations. And so trying to prove it, right, so the first thing to say is that what you need to apply to put this in the accessible setting is Mackay and Bray have this theory of accessible fibration. So if you have an accessible pseudo-functor, if you have a pseudo-functor whose fiber from a accessible category, whose fibers are accessible, and whose base change maps are also accessible functors, then you need one more condition to have an accessible total category. And the extra condition is that the pseudo-functor preserves or sends these filtered colimits to homotopy filtered limit, or to filter bilimits. And if you work out what that actually means in the examples we were looking at, it says exactly like things like Lallies, or a filtered colimit of Lallies is a Lally. But if you think about what you really need for that, it's this homotopy limit. You need the lambda filtered colimits or homotopy limits. So that's actually where the importance of this condition comes from. And then we just realized, well, if you can sort of get rid of the fibrations and do things representatively using this condition, and we eliminated it. But the Grothendieck fibration stuff is ready to be incorporated as soon as. Yeah, it sounds like, yeah. I mean, I saw that you have in the paper you talk about some infinity cosmoi such that the underlying functor is a Grothendieck fibration. So, of course, if there, maybe we can try and put something in at that level. But obviously, if there was a notion of fibration of infinite Grothendieck fibration of infinity cosmoi, that would also be interesting to see, and we could put that in. But yeah, so thanks for mentioning that. All right, so any last questions, comments? Well, if not, then thanks again for coming, and I'll stop recording. So, yeah.